Hello, in this video we're going to talk about the definite integral. So when it comes to look at this graph represents a car driving at a constant speed at 40 miles per hour. So how far does the car travel? Did the car travel? So we know that the distance equals to the speed times the time. And we know that the speed is equal to 40. Right, the graph because it's constant, it didn't change for the car travel for 4 hours, so times 4. So the total distance the car travel is 160 miles. So now if you take a look, 40 is the width, 40 is the height of this triangle. Oh, not triangle, I'm sorry, rectangle. And then 4 hours is the width of this rectangle. So that means their product is the area of this region. Okay, so now here's another example. The car. So here is another example. Suppose that the car travels so that its speed increases steadily from 0 to 40 miles per hour for 2 hours. And how far has this car gone? Well, if you look at here, the trouble with our old reliable distance equals to rate times the time relationship, it's that only works if the rate is constant. If the rate is changing, like what we have in here, this isn't a good way to use the formula. However, if you look at the last example again, we know that the area of the rectangle, the bounded region, is the distance, right? So that means here would be the same. This bounded region, bounded by fx, which is the speed function, and the time x equals to 2 and x equals to 0, and the x-axis is going to be the distance of the car travel. So in this case, we get the distance is going to equal to the bounded area or the bounded region, which is the area of the triangle, half times the base times the height, which means 40 miles. So, but we know that in reality, the rate or the speed is not going to be a constant or have a increasing steadily at certain rate. It's more like a curve. That means sometimes you may climbing uphill or going downhill. So your speed is more like a curve. And sometimes I may ask you, hey, how much did you travel? Not just from 0 to 4 hours in the past 4 hours. Maybe I want to ask you how much you've traveled in the last 2 hours. So that means I'm trying to ask you, hey, what's the area of this bounded region when the time equals to 2 to the time equals to 4? Well, in this case, we are going to use the new method we're going to talk about. It's called Riemann sum. So what is Riemann sum? So Riemann sum method is to build a several rectangles with base on the interval a to b and the side that reach up to the graph fx. Then the area of the rectangle can be calculated and added together to get a number called Riemann sum of fx on a to b. So here is an example. In here is the graph fx equals to 1 over x. And then I want you to find the region, the bounded region, bounded by the graph fx equals to, use the right one, fx equals to 1 over x, and then x-axis vertical line x equals to 1 and x equals to 5. So by the Riemann-summed method, that means I'm going to break these into a multiple rectangle, such as this is the first one, second one, third, and fourth. Okay, so now what are we going to do is we're going to use the left endpoint method. So that means that we know that the width is equivalent, right? All the width is equals to 1 of each rectangle, but the height is, we don't know. So the height, if you look at the rectangle, by the left endpoint method, that means we're going to use the left endpoint as the height. So for the first one, in here, so the area of this block is going to be this one. And then the area of the second block, is going to be on the left endpoint of the second block, which is at 2, 1/2, and then block in here. And then the area of the third block is going to be in here, this one. And then the area of the third block, it will be in this block. Okay. So we divide the region into 4 blocks, and the area is going to be in the sum of each of these blocks, which is equals to the area, area going to equals to the first block 1 times 1 plus 1 times the height, which is 1/2, 1 times 1/3, 1 times 1/4. Which is 25/12, approximately 2.08. Alright, so this is the left endpoint method. So if we have a left endpoint method, that means we also have a right endpoint method. It's similar to what we have. So for the first one, we know that each of these points, for the first block, it will be in here, which is the right endpoint is 1/2. For the second one, the second block is this one, and the right endpoint in here is when x equals to 3, y equals to 1/3. And then for the third block, the endpoint is going to be 1/4, and the last one, the endpoint, is going to be 1/5. So that means the area of these right endpoint methods is going to equals to 1 times 1/2 plus 1 times 1/3 plus 1 times 1/4 plus 1 times 1/5, which is 77/60, approximately 1.28. So now if we compare to these two methods, what did you find out? Well, the sum of the area, if we use the left endpoint method, we know that it's above the curve. There's some area, like this part, is above the curve. And if we use the right endpoint, there's some area is below the curve. So which one would be more accurate? Well, maybe if we take the average of both these two, we will get a very close approximation answer to the area of the curve that we are looking for. Okay, so if we take average, we have 25/12 plus 27 over 60 divided by 2 gives you 101 over 60, approximately 1.68. In general, the average of the left hand and the right hand estimate will be closer to the real area than either of one of these individual estimates. So if you're using a graphing calculator, you will get the actual area is 1.61. So that is, if we're taking the average, it's already close enough. So those sum of the area are called Riemann sum. So here is the definition of Riemann sum. Fx over the interval from A to B is the sum of the rectangles that approximately that are under the curve. So that means the first region, which is Fa of x, plus the second region, the second block. This is how you interpret it. So consider this is your first block, and this is the area of your second block. This is the area of your third block, and go on. This is, let's say, in our last example, this would be fourth block. But in reality, is you don't need to divide it into fourth block. You can divide it into multiple blocks, such as 10 block, 11 block, 21 block. That's totally okay. And each block, the width doesn't have to be equal. So for our example, I make each one is equal to 1 because it's easier for me to calculate. If you think about a graph, look like this one. And I want to divide them into multiple blocks, like 1, 2, 3, 4. With different width and different height, that's totally okay. But remember, each one, like say, this is f of x1 if a left-hand method, and the differences between the x1 to x2 would be delta s1. So if for left-hand method, this is going to be fx1 times delta x1. That is the length times the width. If you let fx1 equals to the right-hand side, that's also okay. So in reality is, when we're doing this Riemann sum, it doesn't matter you use the left-hand one or the right-hand method, because if you divided the subinterval multiple enough, your function is going to be very accurate. Okay, so for the notation of Riemann sum, it's going to be, I'm going to introduce you this. The sigma means the sum, because you have 4 region or nth interval, add them together. So from I, f of xi interval times the delta xi from I equals to 1 to n. That means you divide it into n rectangles, and the sum of these rectangles is going to be the Riemann sum, which is the total area of the bounded curve region. So another definition is definite integral. So a definite integral of a positive function fx over the interval from a to b is the area between fx, x-axis, x equals to a, and x equals to b. So in here you see the curve, you see the curving graph, and the definite interval is going to be the region from A to B bounded by x-axis, x equals to A, x equals to B, and the curve. So this is the definite integral. So the notation for the definite integral is going to be this is a sign for integral sign from A, integral sign, it looks like a little bit like an x, from A to B, f of x dx. So the ds tells us that which variable is. In this specific example, it's going to tell you that, hey, the variable is x. or it doesn't have to be x. Sometimes, for example, if we have our velocity versus time, so the integral, we're trying to figure out when you travel from 0 to 4 hours, and then velocity function, the d should be t because our variable is time. So in algebra, how do we represent this integral, the definite integral region? So remember that the Riemann sum is when I equals to 1, fx1 delta x1. So when do you think not S1. So when do you think this is going to be the most accurate? And how many subinterval you need to divide it to make this very close to the actual area? Well, it has to be the more the subinterval that you have, the more that you're going to give you an accurate answer, right? So that means if the number of the subinterval close to infinite many, so we will get a very accurate answer. In fact, the infinite many of the Riemann sum is going to be our integral from a to b, integrating the function. Okay, now let's take a look at this example. So the graph shows that y equals to RT, the number of telephone calls made per hour on Tuesday, approximately how many calls were made between 9 to 11, express this as a definite integral, and approximately with the Riemann sum. Okay, so now let's take a look. So we know that y-axis is call per hour, calls per hour, and then x-axis is hour. So if you multiply these two, what you get is the numbers of calls. So that means the area represents the total number of calls from 9 p.m. to 11 p.m. So how do I express this in a definite integral? Well, I know the donation is a longer s. From 9 to 11 on the curve RT, so the variable is t. So this is the repetition, the expression of the definite integral. And how do I approximate this with a Riemann sum? Well, you can use a left-hand method or right-hand method to choose the left end point method or right end point method to choose which one you want it to be. So for example, if I use the left hand, the graph look like this one. So I will have from 9 to 11, and then this is 10, 100 calls, and this is 200 calls. I can divide this into 4 intervals because this is just an approximation, so you don't have to be super accurate. So that means each width of the interval is going to be 0.5 hour, right? If I use the left hand method, so that means I need to have a region in here, this one, also these ones, right? So totally 4 blocks, and then I add this block together will give you an estimation of this region. So since this is approximation, I would say this is 100 times 0.5 plus, let's say this point is 150 and this point is 118. So I have a 150 times 0.5 at 118 times 0.5. This one maybe is 195 times 0.5. It gives you over between the time interval from 9 p.m. to 11 p.m. you're totally receiving 313 calls approximately. Now let's take a look at another example. So describe the area between the graph fx equals to 1 over x, the x-axis, the vertical line, and equals to x equals to 1, and x equals to 5 as a definite integral. So I will have from x equals to 1 to 5, the function is 1 over x, the variable is x. So let's have another example. The table shows the rate of population growth between the Barre town for several years. Use this table to estimate the total population growth from 1970 to 2000. So the rate of population growth, RT, is thousands of people per year. That's your y-axis, and the x-axis is year. So first of all, you need to multiply this together and see if they will give you the estimation of the population. So I know that the rate is thousands per people, thousands of people per year. And then if that is your height of that rectangle and the width is the year, if you multiply them, you will get thousands of people. Yes. So that means we need to use the Riemann sum on the integration to calculate that. So that means the Riemann sum from 1917 to 2000, the function fx d of, I should use t. The population over t should equals what? So now let's use the left endpoint. So since each width of the bin is 10, so if it's left endpoint, we will have 10 times 1.5 plus 1.9 times 10 plus 2.2 times, not plus 10, times 10. Sorry about that. So this is equal to 56,000 of people. And now if we use right endpoint method, we will have 10 times 1.9 plus 2.2 times 10 plus 2.4 times 10 equals to 65. And now we're taking the average of these two. I have 56 plus 65 over 2. This is equal to 16.5. Now our best estimate of the total population growth from 1917 to 2000 is 60.5 thousand of people. So now let's talk about signed area. So the signed area is the definite integral of a function fx over an interval a and b is the signed area between f, x-axis, x equals to a, and x equals to b. So So now we have two possibilities. One is the function is always above the x-axis. So your signed area is going to be this region, right, from A to B. But what if the graph is like this one? Sometimes it has up and down. So let's say this is B, this is A. So the signed area is going to be the sum of these four areas. The first one, second one, and the third one. Okay, so the area, this is going to equals to the signed area from A to B, fx equals to the area above x-axis minus the area above y-axis. Below, I'm sorry. The area below x-axis. So that means this is going to equals to the region of 1, 2, 3. This is equals to 1 minus 2 plus 3. The area of the first region minus subtract the second region plus 3. So how do you interpret this one? So you think about it. If this is the velocity, if this graph is related to velocity, so if you have a positive velocity, that means you go into your destination. If you have a negative velocity, you can think about that, hey, you turn around, go back, right? So that means if you're going back, that means the distance that you travel from where you begin is getting less, right? Maybe you forgot something, you need to go back home to pick them up and coming back. So that means your total travel time, the total travel distance should be from your home to the destination. We need to take out of what you've done when you're doing that turn back and get back on. So that's why the total travel area should be all the positive area subtract the negative area. So now let's look at this example. From 1918, there were 12,000 ducks nesting around the lake, and the rate of population changes in the duck per year shows in the figure here. Write a definite integral to represent the total change in the duck population from 1918 to 1990 and estimate the population in 1990. Alright, so now let's take a look. So the integral is going to be from 1918 to 1990, right? And then what will be the change? Well, it has a changing rate of negative 200, right? And then this is the x. Okay, so this should equals to the region of the yellow region, right? Which is the area of the yellow region, which is negative 200 times 10, which is negative 2,000. So that means over that decade, the number of the ducks decreased 2,000. But originally, the population of the duck is 12,000, right? If you're decreasing another 2,000, so that means by the time 1919, the population of the duck should be 10,000. Okay, so here is another example. So using the graph to calculate the integral from 0 to 2 fx, 2 to 4, and 4 to 5, and 0 to 5. Okay, so integration from 0 to 2, I know that the area is equal to 2. So that means the answer from 0 to 2 integrating the fx should equal to 2. And then if I integrate in from 2 to 4, fx is equals to, it's below the x-axis, and the area is equal to 5. So this should be negative 5. Remember, below the x-axis should be negative. And then from 4 to 5 should be fx dx equals to positive 2. And now what about the total integral? From 0 to 5 fx and integrating with x. I will have 2 minus 5 plus 2, which is negative 1. So another way to do integration is you use a graphing calculator. I'm going to show it into another videos. Okay, so that's it for today. I'll see you next time.